Today, we'll be starting off with a topic known as wave interference. And we'll be doing two source interference. So in this chapter, we'll be talking about understand what is meant by the term coherence, path difference, and interference. Then we'll interpret the relationship between phase difference and path difference and explain some examples of wave interference as well. So we saw that wave meeting at its own reflection would stand up a standing pattern known as an interference pattern. And reflection is a convenient way to generate coherence wave because it's one source. And when it's going to reflect back, the same wave is just going to reflect back. तो वो तो coherence है. Coherence mean the wave with the same amplitude है. अब एक ये wave जाई थी and it reflected back as well. Now both the waves are
Right.
the same amplitude, same frequency, same wavelength, everything. However, any combinations of that have the same frequency and a constant phase relationship will produce this result. For example, in figure A, the loudspeakers are connected to the same signal generator, so they simultaneously produce identical sound waves. And wherever the sound waves meet, they will superpose to produce a resultant displacement of air molecules, which means that there will be points of maximum amplitudes, antinodes such as position X or points of zero amplitude, and nodes such as silence. Now, when you look at a wave,
Right.
okay, this is a wave, and
Mm-hmm.
this is another wave. These 3 points are known as nodes where there is a zero displacement, whereas the maximum displacement points are known as antinodes. Got it?
Right.
Nodes represent zero displacement. Antinodes represent maximum displacement. Now look at these two sources. Okay, this is one source wave and this is the other source wave. Look where they are interfering at this point. यहाँ पे interfere करें.
Yep.
Then where else are they interfering? A bit over here.
They idly turn the side as well and up
Exactly.
top as well.
In there as well. Okay, they are interfering in these points. Now these are two loudspeakers generating the same frequency sounds. And now what is two slit interference? So now can you tell me what is interference when you look at this loudspeaker diagram?
When they uh, I don't know how to explain it, but when they overlap each other,
Overlap.
by yes.
Good. Okay. All right. So another interference pattern can be observed if light is shown into an experimental setup that causes it to create two coherent wave sources that produce a standing wave pattern. This effect was first demonstrated by Thomas Young in 1803 using sunlight as a light source and a simple laboratory setup using a torch as well, similar to that shown in figure B, which would also show a pattern of dark and light fringes that resembles the nodes and antinodes in the standing light wave. Young also explained his experiment using a theory that light behaves as a wave, and in classical physics, interference is a phenomenon that can only occur with waves. Young's theory was highly controversial at the time as he was contradicting Newton's theory that light behaved as a stream of particles, and despite the experimental evidence he demonstrated, most scientists at that time refused to believe Young's wave of theory of light. Now, this is an example of interference. You can see यहाँ पे interfere कर रहे हैं. Then you can see over here, they are interfering as well. Now, if you look closely, ठीक है, और कहाँ पे जगह यहाँ पे interference हो रही है. Over here, they are meeting and you can see all those points. This is a picture of a ripple tank where waves are diffracted through two gaps, which will cause an interference pattern between the two water waves. Another common experimental demonstration of two-slit interference is with the laser light as well. Now, if you want to ensure that the wave source is coherent, you can also produce a double interference by using a single source but two slits. ताकि that single source can divide into two, and when they pass through the gap, okay, they are now interfering as well, and now they are producing a bright spot, a dark spot, a bright spot, a dark spot, bright spot, dark spot, and another bright spot. Now all the points where there is a bright spot means that over here the two waves constructively interfered.
Okay.
And all the places where you see no light, the gaps, they are known as the dark regions. That means that the two waves did overlap, but they overlapped or interfered destructively.
Right.
Got it? For example, I'm going to make all the crests first. These are the crests. These are all the crests. ठीक है? ये मैंने 4 crests बना दिए. And now I'm going to make any crest as well of the other wave. These are the other waves, crests. ठीक है? Got it? Now I'll
Right.
draw troughs as well for both the waves. ठीक है? So ये इसका भी trough डाउनलोड कर लेते हैं, मेक कर लेते हैं. So you can see the red dots show what? The troughs.
Yeah.
ठीक है? And the black line shows the crests of both the waves. Now where the two crests are meeting, because what is constructive interference? जब एक का crest और दूसरे का crest दोनों सामने हो, ठीक है, और ट्रफ के सामने ट्रफ हो,
Hmm.
ठीक है, क्रेस्ट क्रेस्ट जब सामने होंगे, so it's
And
gonna
they
be
would line
constructive.
up.
Exactly. So we can see that this is the point where crest crest are meeting. Then this is also another point where crest crest are only meeting, and the middle point is the one where crest crest are meeting. So this would be known as zero order maxima. Maxima means bright region, constructive interference. And these two would be the first order maxima, the first order bright regions. Got it?
Right.
Now, if you look closely at the diagram, I'll zoom in. There are also points where the trough and crest are meeting. For example, look at this one, right?
Yeah.
This is the point of first order minima. No, this is second order minima. First order यहाँ पे आएगी. You look at this crest and trough
Mhm.
meeting. This would be what?
The
First
minima where they
order
would
minima.
cancel out.
Good. यहाँ पे second order minima. फिर यहाँ पे भी देखिए. You can see
Also
crest
second.
and trough meeting. ठीक है? तो ये भी क्या है? First order minima. Got it?
Yeah.
फिर आप यहाँ पे देखो ओवर हेयर एज वेल. ओवर हेयर ये क्या है? दिस इज गोइंग टू बी द सेकंड ऑर्डर में क्रेस्ट एंड ट्रफ आर मीटिंग. दिस इज सेकंड ऑर्डर मिनिमा. क्लियर?
Yeah.
सो ऑन अ समरी, minima means what? A dark region. And a dark region means that the two waves have destructively interfered. Maxima
Right.
means bright region where the waves have constructively interfered. Got it?
Right.
So each point in a two-source interference pattern will have a superposition results that depends on the phase difference between the waves coming from each source to that point. That phase difference will in turn depend on the relative distances to the point from each of the slits compared with the wavelength. In figure E, imagine the distance from slit to X along the blue line, which is 100 wavelengths, and the distance along the red line is 115 wavelengths, as the path difference is exactly 15 wavelengths. The wave will be in phase at point X and will constructively interfere to produce a maximum resultant as in an anti-node. So that would show a bright
What's
spot,
an antinode?
the maximum displacement point on a wave.
The highest point possible. The crest.
Yes. And the zero displacement points are known as nodes, nodes, nodes,
Right.
antinode, antinode. ठीक है? A complete wave always has 3 nodes, 2 antinodes. Alternatively, imagine the blue line distance x is 97 wavelength, but the red line distance is 98.5 wavelength. अब ये कुछ चीज आएगी part difference की भी. Here you can see as well. Can you tell me what's the difference that you can see in constructive and destructive interference over here? You can see that
Uh,
constructive interference का
yeah.
blue line is what?
The district. No, that's the
Crest.
where they overlap.
ठीक है, वो crests है. So you can see where all the blue line crests and are meeting with the crests. That is
They
constructive.
become minima.
Good. Maxima. When crest meets crest or trough meets trough, that is what?
Or maxima, but I'm talking about.
हाँ,
Okay.
minima कहाँ पे
Yeah,
होगा?
I was talking about minima
Over
where
here.
they
When
cancel
the
out.
dotted line is meeting with the bold line. Got it?
Yeah.
Good. Oh yeah. The connection between the phase difference and the part difference comes, no need to do the part difference phase difference now. So what is interference? Interference is the superposition outcome of the combination of waves where an interference pattern will only be observed under certain conditions such as the waves being coherent. Got it? अब phase differences कैसे हो सकते हैं when we talk about constructive interference? Phase difference आपके पास या तो होगा 0 का or it would be 360 when you want a constructive interference, a maxima and a bright region. Got it?
Okay.
And if you need, and if the phase difference is 180 or 270, you would get destructive interference, minima, which is a dark region. Got it?
Okay.
And the values for path difference, if you want constructive interference, path difference would be in whole numbers. How? 1 lambda, 2 lambda, 3 lambda. लेकिन if it's destructive interference, तो values किस तरह होगी 1 by 2 lambda, 3 by 2 lambda. Got it? 5 by 4 lambda.
Yeah.
इस तरह से होंगे when we talk about destructive interferences, और whole numbers में कब होंगे when you talk about constructive interferences. Is this clear? Got it?
What? Can you say it again? Yeah. Wait, say it again. I
The
didn't
part
understand.
the path difference is the difference in the wavelength of the two waves. So if the difference in the wavelength of two waves is in whole numbers, such as 1 lambda,
Okay.
2 lambda, 3 lambda, it's gonna be constructive interference maxima in bright region. But if the
Okay.
difference of wavelengths between the two, इनको हम part difference कहते हैं, if it's not in whole numbers, fraction या decimals में 1 by 2, 3 by 2, 5 by 4, that would give you what? Destructive interference, minima,
Minima.
and dark regions. Or phase
Right.
difference, we
Okay.
already know 0 and 360 means constructive interferences, 180 and 270 means destructive interferences.
Yeah.
Good. Let me show you one thing. The two slit interference. Where is it? Okay, got it.
Young's double slit experiment looked a little something like this. You've got a barrier with two holes in it, but these holes are so small and so close together we characterize them as slits, and double because there's two of them. Young was the English physicist who first did an experiment of this kind, and what we do nowadays is we take a laser and we shine this laser at the double slit. Now the laser has to be wide enough that it hits both holes, and you might think, oh my god, you need a big laser. No, you make these holes very close together. That's why you make them really close together, or at least one reason. The other reason is the distance between these holes has to be comparable. It doesn't have to be the same size or smaller, but it has to be around. It can't be a trillion times bigger than the wavelength of this laser light you're sending in here. It's got to be around the same size, or what we're going to talk about here, you won't see. You won't see the interesting pattern that's going to emerge. You might wonder what I've drawn here. What is this? This isn't a wave. That's not, this is a wave right here. I thought these were waves. What are we doing now? Why we got this different representation? And the reason is, when I draw this pretty much just lets me show a wave in one dimension. But that's not good enough. This process is going to be fundamentally two-dimensional. This wave's going to spread out in 2 dimensions. So I can't draw it like this. I have to draw it like this. Now this whole line here, what does this represent? This represents a peak. Everywhere along here is a peak of the wave. So you've got this wave filling up this entire region. These lines represent lines where every point along there is a peak of the wave. What's in the middle? Yep, in the middle would be the trough of the wave, or the valley. So that's what I'm going to use. I'm going to use this representation for the wave. This will let me show this wave spreading out in 2 dimensions better than this one could. I couldn't draw it very well with this one. So what happens? This wave comes in here. This laser light comes in here. Well, that part hits that barrier, it doesn't get through. This part hits that barrier, it doesn't get through. This part hits the barrier, it doesn't get through. The only portion that's going to get through is basically this portion here and this portion here. These are going to be the ones that make it through. And so what happens? What do you see on the wall over here? If this was a screen that you could project the light on, what would you see? Well, naively, what I would have thought, I've been like, okay, shoot, light comes through here, bright spot. Light comes through here, bright spot. You just get 2 bright spots, right? Well, no, that's not what you get. That's why this experiment is interesting, because you don't just get 2 bright spots. You get a pattern over here, because waves don't just travel straight through this hole. When a wave encounters a hole or a corner, it spreads out, and that spreading out we call diffraction. So you're going to get a wave spreading out from down here. So it's not going to go in a straight line. It spreads out in 2 dimensions. That's why I had to use this wave drawing representation. It's going to spread out from the top one too. Uh-oh, look what's going to happen. You're going to have 2 waves overlapping. These 2 waves are going to start overlapping, and where they overlap constructively, you'd get a bright spot. Where they overlap destructively, you'd get a dark spot. Where it's sort of half constructive, half destructive, you might get a mediumly bright spot. How do we figure out what's going to be? Well, I can't draw this precise enough to show you that. So let me get rid of all of this mess real quick. Get rid of that. Out of the bottom hole, what would you get? You'd get this. A nice spherical pattern coming out of here. Now it might not exactly.
Now, can you tell me what do we call these lines? What is the name of that is given to these imaginary lines that we show in this direction?
I have it written down with it was
Mhm. It's known as wavefronts. Got it?
yeah, wavefronts. Wait.
Okay.
Be the same
Yeah.
intensity throughout here, but I can't draw it with the exact right intensity. Up here, this intensity of this portion would be smaller than this portion here, the degree to which it's spreading, but this will help me visualize it. You've got this wave spreading out of the bottom hole. You also have a wave spreading out of the top hole. And now these are going to overlap. Let's draw them both. Boom. Waves overlapping in the same region. You're going to have constructive and destructive interference. And if you look, remember these lines represent peaks. So every time a peak lines up right over a peak, or in the middle, a valley over a valley, every time the wave is exactly in phase when it gets to the same point, these are all constructive points. So right in the middle, you'd get a big bright spot. That's kind of weird. Right in between these holes, there'd be a big bright spot. Where else? Well, look at this. Bright. This is constructive, constructive, all constructive. They form a line. They get these lines of constructive interference. Same with this line, constructive, constructive, all the way over to here. So on the wall, you'd see multiple bright spots down here. These are all constructive because peaks are lining up perfectly. And I'd get another one here. You'd keep getting these bright spots on the wall. They wouldn't last forever. I mean, at some point it'd start to die off. It'd be hard to see. But you'd be getting these bright spots continuing on. At some point they're so dim you can't see them. And in the middle, well, wherever, let's see, what's a good point to look at? Wherever a peak lines up with a valley. So this wave's a peak right here. But for the other wave, look at, we're in between the 2 green lines. So at that point you have destructive because the peak is matching up with the valley, and this would be destructive and this would be destructive. So in between here you get a destructive point. The same is true in between each of these perfectly constructive points. You get a perfectly destructive point. In between those it'd be kind of half constructive, half destructive. It would merge into each other, and what you get, sometimes physicists draw a little graph to represent this. You get a bright spot in the middle. This is sort of representing a graph of the intensity. 0, and then another bright spot, and then it goes down to 0 again, another bright spot. They get weaker and weaker as you go out. At some point it's hard to see. Same on this side, 0, bright spot, 0, bright spot. This is the classic double slit pattern you'll see on the wall, and it's caused by wave interference in 2 dimensions. And what's the rule for wave interference in 2 dimensions? This is the same rule as the wave interference for 1 dimension. It was this. Remember, for 1 dimension, delta x, the path length difference, had to be 0. Lambda, 2 lambda, 3 lambda, so on, would give us constructive interference. And now if you're paying close attention, you might say, hold on. There was a condition. Remember, this was only true if there was no funny switcheroo business with the back of the speaker. We had to make sure that these 2 sources were in phase to start off with. Is that true of these light waves? It is. In fact, that's why we do it double slit like this. That's why we take 1 wave. We let 1 wave come through here. That way, we break it up into 2 pieces. Why? Because we know if a peak was going into the top hole, well, the same wave was going into the bottom hole. That's also a peak. This is a tricky way, a quick, easy way to make sure your 2 sources coming out of these 2 holes are exactly in phase. You don't have to worry about any phase difference caused by the source. You just have to worry about a phase difference caused by the fact that these waves are going to travel different distances to different points. And what do I mean by this? What does path length difference mean here? Well, if I look at from this top line, or this top hole, this is basically like our speaker. One source here, but it's light instead of sound waves. From here to the center bright spot, the wave from the top hole had to travel a certain distance. And from the bottom hole to that spot, wave had to travel a certain distance. So basically this we can call x1, this length x2. And the path length difference would be x1 minus x2. The difference in these, and you can just make it the absolute value if you want, but the size of the difference between these two path lengths. What is that going to be for right in the center? Well, that one's just delta x equals 0, because the waves are traveling the same distance to get to that point. And that makes sense. That's a constructive point because 0 gives you a constructive point when the path length difference is 0. How about the next?
So here you can see कि path difference जो constructive interference में आ रहे हैं वो कैसे आ रहे हैं? 0,
Uh,
1 lambda,
yes,
2 lambda. Got it?
because they are equal
Yep.
in one numbers, so
Yep. Exactly,
they will
you got it.
become
क्योंकि एक one full wave का difference है. जब एक पूरी
yes,
wave का difference
constructive.
होगा, because 1 lambda means what? 360. 0 lambda
Yeah,
means 0. 2 lambda
yeah.
means
So it will
720.
become constructive interference.
गुड, बिल्कुल. क्योंकि फेज डिफरेंसेस के साथ आप इसको रिलेट करो. फेज डिफरेंसेस क्या होते हैं? 0, 360. तो ये पार्ट डिफरेंस वैसे ही है. आइदर इट्स जीरो वेव और इट्स अ फुल वेव, या फुल वेव का डिफरेंस हो या जीरो वेव का डिफरेंस, तब भी क्रेस्ट एंड क्रेस्ट
Right.
वुड ओवरलैप एंड ट्रफ वुड ओवरलैप. अगर हाफ होगी, जैसे 180 होगी, 180 डिग्री, 270 डिग्री, दैट वुड मीन व्हाट? दैट व्हाट्स द डिफरेंस इन वेवलेंथ्स? The other wave is 1.5 times more further than the other wave, or it's 2.5 back behind from the other wave, or it's only 0.5 in the forward direction, या 0.5 ahead होगी, 0.5 behind होगी than the other wave. तो ये जब 0.5, 1.5, 2.5 का difference आएगा, that is destructive. Got it?
Yep.
Good.
Point. Well, the wave from the bottom has to travel this far. The wave from the top hole has to travel this far. This time they're not traveling the same distance. The wave from the bottom hole is traveling farther. How much farther? Well, it's got to be the next one. It's got to be lambda. So this wave is going to be traveling, the bottom wave would travel one wavelength further to get to this point than the wave from the top hole, because that's the next possibility for constructive interference. Note, it's not from here to there that's one wavelength. This is a common misconception. This distance on the wall between constructive points is not one wavelength. The difference in path length that one wave travels to get there compared to the other wave is one wavelength. And I bet you can guess the next one. The next one, delta x, would just be 2 wavelength, and you can keep going. How about the destructive points? Shoot, you know how to do that. These are going to be the half wavelengths, lambda over 2. This one's going to be 3 lambda over 2, and so on. And down here, what would you get? Well, if you got rid of the absolute value sign and you wanted to, you could start talking about this delta x would be negative 1 lambda. This one would be negative 2 lambda, and so on.
But you don't have to care about signs. These signs are done in Cambridge. You're in Edexcel. You don't even
Right.
need to get into that science. All you need to know
Okay.
that ऊपर भी first, second, third order, नीचे first, second, third order. Forget the science. Science is not even included in your syllabus. Got it? ऊपर भी
Okay,
1 है, नीचे भी
okay.
1 है. ऊपर भी 2 है, नीचे भी 2 है. That's all. No plus minus sign. Don't listen to that stuff. ठीक है? That's what you need to know. So what is the differences in phase difference and part difference between constructive and destructive interferences? Can you explain me?
Wait, say it again.
What is the difference between the phase differences and part differences of constructive and destructive interference?
Constructive interference have whole numbers and would either have a degree of 0 or 360,
Good.
while destructive interference will happen in odd numbers like 0.5, 0.75, and it will have either 180 degrees or 270.
Good job. Good. Okay. So let's discuss the phase differences and part differences as well now.
If two waves overlap in the same medium, we say that there's wave interference. So this box here could represent a speaker, and this could be the sound wave it generates. Or it could represent a laser, and this would be the light wave it generates. Or it could be some sort of ripple tank generator, and this is the water wave it generates. Regardless, if you had a second source of a wave and these were to overlap, you'd cause wave interference, and what that would look like would be something like this. So let's say these are speakers. I like thinking about it in terms of speakers. I think it's easy to think about. And I put this speaker right next to the first speaker, side by side. So they'd be creating sound waves in this region. And I wouldn't really have two sound waves necessarily. You can think of it as just having one total sound wave. And how would we find the size of that total sound wave? Well, if I put an axis in here, the axis will make it easier for me to think about this. I'm going to put an axis through here like this. What I can do is I can just ask myself this. I'm going to say, what was the value of the first wave? So I'm going to take that value. What was the value of the second wave? And I'm just going to add them up. To get the value of the total wave, I'd take that value of the first wave plus the value of the second wave, and well, I just get double in this case. And I can come over to here, okay, value here plus the value there. I get double that point. It's not going to be as high because they weren't as high. And then over here I got 0, and 0 is just 0, and you start to see what's happening. I can come down here, very low or very negative, and I get double that down here. And if I were to trace this out, what I'd get is one big total sound wave that would look like this. So these have been amplified. So that's one possibility. When two waves overlap, you can get this case where the peaks match the peaks and the valleys match the valleys, and you get constructive interference. So notice how each valley matches the valley, each peak matches the peak, and this is called constructive interference because these constructively combine to form one bigger wave. So this is constructive interference. So what would you hear if your ear was over here somewhere waiting to hear this sound? What you'd actually hear is a loud note. This would be much louder than it was. It'd be twice as loud, in fact, which makes sense. You've got a second speaker in here. It's twice as loud. That makes sense. What's a little bit harder to understand is you can also have something called destructive interference. What would that look like? Well, imagine you had two speakers, but they looked like this, so that the peak of the first one lined up not with the peak of the second one, but with the valley of the second one. And the valley of the first one lined up with the peak of the second one. These are out of phase, we say. Before, when they looked like this, these waves we say are in phase because they look identical. The peaks match up with the peaks, the valleys with the valleys. These are out of phase. How far out of phase are they? We say that these are 180 degrees out of phase. So these are 180 degrees out of phase. The phase refers to what point on the wave cycle is the wave at. And these two are starting completely separately, which is 180 degrees. You might think that means 360, but think about it. If you turn around 360 degrees, you're actually back to where you started. If we tried to make these 360 degrees out of phase, they'd look identical again because I've moved one so far through a cycle that it's back to where it started in the first place. So I want to move it 180 degrees out of phase. That's exactly the opposite, so that you get peak lining up with valley, or if you like radians, this is called pi out of phase because pi and 180 are the same angle. All right, so what happens here if I take these two speakers, and if I take this second speaker and I line it up right next to the first speaker, I get something that looks more like this. Look at how weird this looks. These are completely out of phase, and what's going to happen is if I add my little axis to help me think about this, I'm not going to add an axis straight through here. Now I play the same game. What total wave do I end up with? Well, I take this value. I'm going to add up the values just the same. I take the value of the first wave plus the value of the second wave. I add those up. One's positive, one's negative. I get 0. And then over here, 0 plus 0 is 0. And then the valley of the first wave's lining up with the peak of the second wave. And if I add these 2 points up, I get 0 again. And you probably see what's going to happen. I'm just going to get a flat line. I'm going to get a flat line, and I'm going to get no wave at all. These two waves cancel. And so
So why do these two waves cancel? Because the crest is meeting the trough of the other wave. Got it?
Yes,
तो
exactly.
वो
And they're
उनको
out of
कैंसिल
phase.
होकर
So,
डिस्ट्रक्टिव बना देती है, 180 डिग्री का फेज डिफरेंस है।
Call
yeah,
this
exactly.
not constructive interference, but destructive interference, because these have destructively combined to form no wave at all. And this is a little strange. How can two waves form no wave? Well, this is how you do it. And what would our ear hear? If we had our ear over in this area again, we were listening. If I just had one speaker, I'd hear a noise. If I just had the second speaker, I'd hear a noise. If I have both the first and second speaker together, I don't hear anything. It's silent, which is hard to believe, but this works. In fact, this is how noise canceling headphones work. If you take a signal from the outside and you send in the exact same signal, but flipped, pi out of phase, or 180 degrees out of phase, it cancels it, and so you can fight noise with more noise, but exactly out of phase, and you get silence in here, or at least you can get close to it. Now you might be wondering, how do we get a speaker to go 180 degrees out of phase? Well, it's not too hard. If you look at the back of these speakers, let me make a clean view. If you look at the back of these speakers, there'll be a positive terminal and a negative terminal, or at least inside there will be. And if you can swap the positive terminal for the negative terminal and the negative terminal for the positive terminal, then when one speaker is trying to push air forward, there's a diaphragm on this speaker moving forward and backwards. When one speaker is trying to push air forward, the other speaker will be trying to pull air backwards, and the net result is that the air just doesn't move because it's got equal and opposite forces on it. And since the air just sits there, you've got no sound wave because air has to oscillate to create a sound wave, and you get destructive interference. So that's how you can create a speaker pi out of phase. Well, you might be wondering, I don't want to mess with the wires on the back of my speaker. In fact, you shouldn't, so you don't get shocked. But if I've got two speakers in phase like this, then I'm stuck. I can't get destructive interference, but yeah, you can. Even if you don't mess with the wires, and don't try this at home, you can still take this speaker. Remember, before, when these were in phase, we just lined them up like that, constructive interference. But I don't have to put them side by side. I can start one speaker a little bit forward and look at what happens. We start to get waves that are out of phase. So my question is, how far forward should I move this speaker to get destructive interference? And we can just watch. So I'm just going to try this, and when we get to this point there,
तो अब जो ये वाला पॉइंट है, दिस इज व्हाट 180, क्योंकि हाफ वेव आगे
Yes.
चला गया, देयर इज अ डिफरेंस ऑफ हाफ वेव, द सेकंड वेव इज 0.5 अहेड ऑफ द फर्स्ट वेव, तो ये आउट ऑफ फेज हो जाएगी, क्रेस्ट बिल्कुल
Yes.
ट्रफ के सामने आ गया, गॉट
Yeah.
इट?
now we're out of phase. Now I have destructive interference. And so how far did I move my speaker forward? If we look at it, here was the front of the speaker originally, right there. Here's the front of the speaker now. If you look at this wave, how much of a wavelength have I moved forward? The amount of wavelength that you had to move forward was 1/2 of a wavelength. So if you take two speakers that are in phase and you move one half of a wavelength forward, you get destructive interference again. Again, if my ear is over here, I'm not going to hear anything. Even though these two waves started off in phase, move 1/2 a wavelength forward, they line up so that it's destructive, I get no noise. But if I take this away, we go back to the beginning here, take my speaker, we start over. If you move it forward a whole wavelength, so I take this here, keep moving it, whoop, destructive interference, and now, whoa, here we go. Constructive interference again. That's a whole wavelength. So if you move it forward a whole wavelength, look at one whole wavelength forward. So the front of the speaker was here. Now the front of the speaker's here. This is an entire wavelength. I get constructive interference. Now I'm going to hear a loud sound again. I'm going to hear twice the noise that there would be if I just had one speaker. So the moral of this story is that even if you have speakers that are in phase, you can get constructive or destructive interference depending on the difference in length that these two waves travel. In other words, wave 2 is traveling this far to get to my ear. I'm going to call that x2. And wave 1 is traveling this far to get to my ear. I'm going to call that x1. If I took the difference between these two, I'd be finding the path length difference. The difference in path lengths that these waves are traveling, and that would be this amount. This is the difference right here. I'm going to call it delta x, because because it's the magnitude of the difference between these two lengths. And we saw that if this equals lambda, it was constructive. And if it equaled a half lambda, it was destructive. But those aren't the only values. We can write down an important result here. If delta x, the path length difference, was lambda, or it turns out 2 lambda will work, or 3 lambda. Imagine moving the second speaker one more whole wavelength. Well, you'd be perfectly back in phase again because you'd align back up perfectly, or 3 whole wavelengths. Again, perfectly in phase. Any integer wavelength, including 0, because 0 is just the case where the speaker was right next to speaker 1, where these two speakers were lined up right next to each other. You'll get constructive interference. The waves line up perfectly, it's going to be constructive. And we saw if delta x equals a half wavelength, it was destructive, but that's not the only case. Any odd half integer here, so I can't do 2 over 2 because that would be lambda again. I can do 3 lambda over 2, or 5 lambda over 2, or 7 lambda over 2. Any of these will give me destructive interference because they'll cause these peaks to match up with valleys. The whole thing would flatline. I'd get no sound. This is an important result. If you've got two speakers that are starting off in phase, in other words, they both start off the same way, and by that I mean one speaker sends out its wave, one speaker sends out its wave going up, the other sends out its wave going up, they're both at the same cycle. If the only difference is the path length difference, this is an important result that lets you determine whether there's constructive or destructive interference. But you might ask, hold on, what if, see, this was assuming there was no phase difference to start off with. What if you...
So now you can tell the different angles, the phase differences of constructive destructive interference as well, and the path difference of constructive and destructive interference as well. Is it clear?
Yeah. Yes, I think so. Yeah.
And that is all for today. Your topic number 3B4 is also completed. We are done with topic 3B. Tomorrow we'll be doing tomorrow and Thursday. Wednesday and Thursday, you'll solve all the questions of 3B from the book. 3B1, 3B2, 3B3, 3B4. Then we'll move on to topic 3C on Saturday. And before that, you'll also get some recorded lectures for topic 3C and 3D. Got it?
Yep.
All right. I'll see you next time. Goodbye. Love.
Yes. See you on Saturday.
Good.